In section 1.6, we will look at some other types of equations that you should know how to solve or will learn how to solve. The first one we'll speak about is rational equations. A rational equation, that will be what goes in the first set of blanks. A rational equation is an equation that has a rational expression for one or more terms. Now you may be wondering, what does that mean? The word rational has ratio as its root, and if you recall, a ratio is a way of comparing two things. It's another way of saying it's a fraction. So we're going to be looking at equations where there are fractions involved. This time we will see variables in the denominator, unlike some of the equations that we looked at back in section 1.1. Now to solve a rational equation, we're going to use that same method we used in 1.1. We will multiply each side by the least common denominator. The least common denominator. And that way we can eliminate fractions, and then we'll be able to solve the resulting equation. So this is very similar to what we did in section 1.1. But there's one key difference that will happen now, since those variables will appear in the denominator when we come up with a solution. Remember, it's a proposed solution, and we have to remember when working with fractions that we cannot have 0 in a denominator. So we have to take the answer that we get and go back to the original equation to look and make sure that it would not cause the denominator to become 0. If it does, that means it's not a valid solution and we can't use it. So let's go through a few examples. These will be equations that lead to linear equations when we eliminate the fractions, which means we're not going to have an x squared as part of what will remain when we solve. Now, in order to find the LCD, we're going to use the same process that we do when we have just numbers in the denominator. For example, if I had the fraction 1/2 and I wanted to add the fraction 1/3 to it, what I would look at first is to see, do those denominators match? Because if they do, I already have a common denominator, and that is my LCD. Obviously, these do not match. The next thing I want to ask myself is, would there be a common factor for these two denominators? Is there anything other than 1 that would divide into each evenly? And there's not. 1 is going to be the only common factor. So if they don't match and they don't have any common factors, I would simply multiply them together to get my LCD. Keeping that principle in mind, as you look at A, one of our denominators is 2, the other denominator is x plus 1. Now, the x plus 1 is different not only because there is a variable, but there's also 2 terms. So I would need to ask myself, obviously these two do not match, so I know I don't already have a common denominator, but I would need to see if the expression that has 2 terms is something that could factor. If I have a common factor that can be removed, it might match the denominator that's in the other fraction. But obviously x plus 1, they don't have a common factor between them except for 1. So I have 2 fractions and the denominators do not match. The denominators do not have any common factors. That means my LCD will have to be the product of those two. It will be 2 times x plus 1. Now, instead of using the distributive property, we want to leave it in factored form, because remember, our goal will be, we take that LCD and we are going to multiply every term in our equation on each side of the equal sign. We have to multiply every term by this LCD. So this first fraction gets multiplied by 2 times x plus 1. The second fraction gets multiplied by 2 times x plus 1. And notice on the right, I don't even have a fraction, but it doesn't matter. It still has to be multiplied by the LCD, 2 times x plus 1. It just means nothing is going to cancel out on that side because I don't have a denominator that will have a common factor with any part of this LCD. Now we go through the same process we did in section 1.1. I'm noticing in the first fraction I have a 2 in the denominator and a 2 as part of that LCD in the numerator. Those can cancel out. Remember, if it helps, look at it as that LCD over 1, so it looks like a fraction times a fraction. Now be very, very careful here, because what's left is 2 binomial terms that need to be multiplied together. In other words, you're going to need to use FOIL or the box method to multiply these back together in a moment. But I don't have a fraction any longer, so that part is nice. The second term, when I look at the factors that could be reduced, I have an x plus 1 in the denominator and an x plus 1 in the numerator. This one is much easier to simplify. When I multiply straight across, I will have plus 10x, because 5x times 2 is 10x. When I look on the right side, I am going to need to use the distributive property. I would encourage you, instead of leaving the x times 2 outside the parentheses, switch the order. We typically would put the coefficient or the number part in front of the variable, and that means we will be using the distributive property on the right side of the equal sign, but we've got to go back and use FOIL or use multiplying with that box method to use the distributive property correctly with 2x minus 3 times x plus 1. If we were to multiply using FOIL, that means first times first. So 2x times x is 2x squared. If I multiply outer times outer, 2x times a positive 1 is plus 2x. Inner times inner would be a negative 3 times x, so that's a minus 3x. And last times last would be negative 3 times positive 1, which is a negative 3. I still have my plus 10x, but I have no more parentheses on the left side of the equation. Now let's distribute on the right. 2x times x will give you 2x squared, and 2x times 1 is 2x. It's time to start combining like terms. I'm noticing on the left side I have several terms that have x in them. I've got 2x minus 3x plus 10x, but I only have one term with an x squared, so I'm still going to have 2x squared. When I combine all of those x terms, 2x minus 3x is a negative x, and negative x plus 10x would give me plus 9x. And then I still have the minus 3 equals, on the right side, I have 2x squared plus 2x. Now it's time to see about getting like terms together that are on opposite sides of the equal sign. And notice what happens to these x squared terms. When I try to combine them, they cancel out on each side. So I do not have any x squareds remaining. If I subtract 9x from each side, in order to get the x's on the same side, I would have minus 3 equals a negative 7x. We'll need to be very careful because we do have negatives here. That means when we divide each side by the coefficient in front of x, make sure you're dividing by a negative 7. And a negative divided by a negative gives you a positive. And that would mean that x is equal to positive 3 over 7. Now, as I box this up, I need to go back and look at the original equation. Because if 3/7, if I try to plug it in for x, would make a denominator become 0, it's not a valid solution and I can't use it. But the only denominator that had an x is the second fraction, 5x over x plus 1. And if I use 3/7 there, I do not get 0 in the denominator. So it's a valid solution. I could actually plug it into the equation and make sure the left side equals the right. It's doable. It's a little messy, but that might be something your calculator could help with if you want to confirm your answer. Now, as we look at the next example, we have something similar in that there are 3 terms involved. 2 of them are fractions, but notice what you have here. When I check the 2 denominators, the first thing I'm to ask myself is, do they match? And the answer is yes. That means I already have the LCD. It has to be x minus 5. As long as those 2 denominators match and I don't have any other denominators that are different, I have found the LCD. So I'm going to have to take every term, both sides of this equation, and we will multiply by that LCD. So we'll multiply the first term by x minus 5. We have to multiply the 5 times x minus 5. And we have to multiply the fraction on the right times x minus 5. Now what happens is on our fractions, the denominator cancels with the LCD. So my first term just becomes x plus, now nothing cancels in this next expression because there wasn't a fraction, there's not a denominator there. I simply use the distributive property and I will have 5x minus 25. As I move to the right side of the equal sign, the x minus 5's cancel, leaving me with just 5. So this is cleaned up very nicely. I do see some like terms on the left. I can add the x plus 5x. That will give me 6x. So 6x minus 25 equals 5. In order to solve for x, I need to isolate that x term. So let's add 25. And that means 6x equals 30. To finish this, when I divide by 6, I get x equals 5. Now remember, before I box it up and move on, I need to go back and look at the original equation. I'm noticing if I try to put in 5 for x, my denominator will become 0, which means I can't use this. It's not a valid solution. Therefore, since it was the only choice I had and it doesn't work, the empty set or no solution is the answer. Let's go to the next page of notes. As we look at the next examples, notice the heading says that we can solve rational equations that lead to quadratic equations. That means our x squareds will not disappear on these. So sometimes they disappear or they were never there and we have linear equations, but we may also end up with quadratic equations. Now, as I look at these denominators, first of all, I have 3 fractions. Each one has a denominator. That's a little bit different. But I also notice that 2 of them, have 2 terms. They're binomials. And remember, if there's more than one term, I need to ask myself, is it possible that it would factor, and maybe if I factor it, I'll have a term that, a factor that is in common with another denominator that already exists. So as I check these denominators on A, the first one is x minus 3. 2 terms, but the only common factor between those 2 terms is 1. Second fraction, x is the denominator. There's nothing I can do with that. But notice the one on the right, x squared minus 3x. There is a common factor, and it is x. So if I factor out an x in parentheses, I would have x minus 3. It's backwards distributive property is the way you can think of it. And now when I start to compare, I'm noticing when I factor that, the x is a common factor with one of the other denominators. The second fraction had a denominator of just x, and the x minus 3 is also in common with the first denominator, x minus 3. Now that I have some factors that match up, when I look for the LCD, I have to use one of every different factor that occurs in these denominators. I only have 2 different factors. I have x and x minus 3. So that becomes my LCD, x times x minus 3. I have to use both of the 2 different factors that occur in these denominators. Now, the rest of this is just like what we have done on the other problems. We're going to have to multiply every single term by this LCD, and I would leave that denominator factored as x times x minus 3, and now if I multiply every term by the LCD of x times x minus 3, let's see what we have left. And the one on the right also has to be multiplied by x times x minus 3. Our first fraction, the x minus 3's, will cancel, and I'm left with x minus 5 times x, which means I'm going to need to use the distributive property. I'm going to put the x first and then the x minus 5 in parentheses, and we'll distribute that in just a moment. Second fraction, the x's are going to cancel, and that means I'll be left with plus 1 times x minus 3. We'll distribute that in just a moment. Now on the right side, everything in that denominator cancels with the entire LCD. That means I only have negative 7 on the right side of the equal sign. Time to do a little more cleanup. Distribute, and you will have x squared minus 5x plus x minus 3 equals negative 7. So we distributed through in both of those parentheses, and I do see some like terms that need to be combined. The negative 5x plus x, if I add those together, I get minus 4x. So I have x squared minus 4x minus 3 equals negative 7. And remember, because it's quadratic, I need to get everything on one side, set it equal to 0, and solve. So let's add 7. That will give me x squared minus 4x plus 4, because negative 3 plus 7 is a positive 4, equals 0. Time to factor. I'm asking myself, if I think through the AC method, a pair of numbers that could multiply to give me positive 4 but add to give me negative 4, well, the only way that can happen is if they're both negative, and if I use negative 2 and negative 2, that will work. Again, I can use FOIL to multiply that back together to make sure that what I wrote as my factored answer is equivalent to the trinomial that we were factoring, and I will get x squared minus 4x plus 4. Remember your zero factor property. Once I have it factored and set equal to 0, the only way this is true is if I set each of those parentheses equal to 0, because these parentheses are the same, they matched. I really just have to set x minus 2 equal to 0 one time, which means I'm going to add 2 to each side, and I get a value of x equals 2. So even though it was quadratic, I only came up with one possible solution, but before I box it up, check the original equation. If I use 2, will I have a problem? In the first fraction, if I plug in here, the 2 minus 3 would not be 0. Second fraction, if I plug in a 2 for x, I'm okay. I'll have a 2 in the denominator. And in the fraction that's on the right, if I plug in 2 for x and clean up, 2 squared minus 3 times 2 would give me a negative 2. I'm fine. As long as I don't get 0, I can get any other number in the denominator, and it will work. So there's one example. Let's look at example B. And again, we should notice we've got two terms in each of these denominators. They're binomials. The first two are not going to factor. X plus 5 has no common factor but 1. X minus 5 has no common factor but 1. But notice x squared minus 25. Because the first term is a perfect square and the last term, 25, is a perfect square, and there is a subtraction sign in the middle, this is a difference of squares. If you need to go back and review those methods for factoring, go to that review video that's loaded in at the bottom of the homework in my math lab, and you will discover that this factors into x plus 5 times x minus 5. When we have a difference of two squares, you open two parentheses. The square root of the first term goes in the front of each parentheses. The square root of the last term goes at the end. And then one parentheses gets a plus and one gets a minus. Well, now that we've done this, same as on the last problem, if I start checking to see if I have any repeated factors, I will see that I do. I only have two different factors that show up. I've got to use one of every different factor. that I get in these denominators, and that means x plus 5 times x minus 5 is the LCD. Now that I have the LCD, I am ready to go through and do a little cleanup. So I'm going to give myself a little space here, and I need to multiply every single term by this LCD that we just found. Remember, leave your denominator in factored form. I ran out of a little bit of room there. Let me see if I scoot over. There we go. Now we'll multiply this first term by our LCD. We're going to multiply the second term by the LCD. And this last term also needs to be multiplied by the LCD. When we get ready to clean up now, I notice the x plus 5's cancel in that first product of fractions, leaving me with x times x minus 5. We'll distribute that in a moment. Plus my second fraction, the x minus 5's cancel, and I have 5 times x plus 5 equals, on the right side, the entire denominator cancels with the entire LCD, and that just leaves me with 50. Okay, let's distribute through and see what we have. We're going to have x squared minus 5x for the first time we use distributive property. When we get to this next place to use the distributive property, we end up with plus 5x plus 25 equals 50. Now, when I go to combine like terms, what happens when I add negative 5x and a positive 5x? They cancel each other out, and I'm left with x squared plus 25 equals 50. Now, you have a couple of choices about how to solve from here, but hopefully you remember from section 1.4, if we do not have a term that it has just a plain x, if the b is 0, but it's quadratic, if I have an x squared and I have a constant, then I can isolate the x squared and use the square root property. So if I were to subtract 25 from each side, I would have x squared equals 25. Now be very careful. Don't forget, when we're using that square root property, we're taking the square root of each side to get just x. We want the square root to cancel out the square. But that means when I take the square root on the right, I have to remember there's both a positive and a negative root. There are two. And that tells me that x could be positive 5 or negative 5. Now, before I box those up, I have to go back to the original problem to make sure I'm okay, that it will not create a denominator with 0. And if I look at the positive 5, in the first fraction, x plus 5 is the denominator, and I'm fine. But when I move to the second fraction, if I plug in 5, 5 minus 5 is 0. I can't use positive 5. It will not work. Let's try negative 5. And if I go to the first fraction and I plug in negative 5 for x, I get 0 in the denominator. I got two solutions and neither one worked. That means no solution is the answer on this equation. So without checking in the equation, you will not know. You have to go back and check to make sure that you don't get 0 in the denominator. Let's move to the next slide. And now we'll talk about radical equations. So as we work with radical equations, we're going to follow some steps in order to come up with a solution. One thing we have to be very careful about with radical equations is, just as we saw we had to check our answers with those rational equations, we will have to check our answers with radical equations, because we will oftentimes get values that won't work. We'll get what's called an extraneous solution. Maybe if we get two answers, one works and one doesn't, and there is no clear way to test it without plugging it in. So we're going to have to plug in those proposed solutions to double check. So here's how we'll approach these problems. First, we're going to isolate the radical on one side of the equation. That means if there's anything else being added or subtracted to that radical, we want to move it to the other side before we try to do step 2, which would be to raise each side of the equation to a power that is the same as the index of the radical. Now, you may question the vocabulary a bit there. What that means is if I see a square root symbol, such as we see in this first example, the index is understood to be 2. If I don't see a little number in the corner, then I know it's a square root and the index is 2, and I can undo a square root by squaring that square root. If there had been an index, we would see a small number in the corner, and we'll see an example of that in a little bit. And then we would have to raise both sides to that same exponent in order to eliminate the radical. Now, it is possible to have more than one radical in the equation. If that were to happen, then we would want to separate the two radicals. We would want to isolate one on each side, and it's possible we might end up needing to go through this process more than once. We're going to look at some specific types of problems, and you shouldn't see anything that would require a different solution method from what we see. So look at this first example. Remember, our goal is to isolate the radical on one side of the equation. That's our step 1. And I'm noticing I have more than just the radical on this left side. X minus square root of 4x plus 12 equals 0. I'm going to have to move something, and I can choose what to move. Hopefully you recognize that it would be advantageous if I actually add the radical to each side, and then both sides will have positives. If I were to subtract the x, I would have a negative on each side. So what I'm going to do is add the square root of 4x plus 12 to each side, and that will leave me with x equals the square root of 4x plus 12. Now that the radical is isolated, notice step 2 says raise each side to a power that's the same as the index. Well, because it's a square root, I understand the index is 2, even though I don't see it. So everything that's on the left side gets squared. That's going to be easy because there was only one term, and everything on the right side will be squared. Well, if I square x, that's just x squared. And remember, our purpose in doing this is we're going to square that radical because the square will cancel out with the square root. They're going to eliminate each other. And all we'll be left with on the right is 4x plus 12. If I square a square root, they will both go away. Now, when I see what I have left, I have a quadratic equation because there's an x squared. It's not going away, so that tells me I need to get everything on one side and set it equal to 0 to solve. So let's subtract the 4x and subtract 12, and we will have x squared minus 4x minus 12 on the left, and that will equal 0 on the right because everything would cancel on the right. And let's see if we can factor this using the zero factor property. So if I multiply the a times c, 1 times negative 12 is a negative 12. I need a pair of numbers that will multiply to give me negative 12, but add to give me negative 4. And I believe if I use negative 6 and a positive 2, I've got it. So x minus 6 times x plus 2, again, if I use FOIL and I double check myself, this would multiply back together to equal x squared minus 4x minus 12. So I have it factored correctly. And then to finish solving, I set each parentheses equal to 0, and I solve. And what I come up with is an x value of 6 or an x value of negative 2. Now, at this point, we need to plug these values into the equation and check to see if they both work. So I'm going to write out the check. You could actually do it in your calculator, but if I were to do this by hand, if I put in 6 for x, this is what it would look like. So 6 minus the square root of 4 times 6 is 24, and 24 plus 12 is 36. I want to see if that would equal 0. Now remember, if the radical is in the equation already, it's asking me for that positive root. So that would give me 6 minus 6 equals 0. That checks. I know 6 is a solution. If I were to go back and use negative 2, and I put in negative 2 everywhere I have an x, then it's going to look like this. And I would have negative 2 minus the square root of 4 times negative 2 is negative 8. Negative 8 plus 12 is a positive 4. And remember, because the radical is there, it's asking me for the positive or the principal root, so that would be negative 2 minus the square root of 4 is 2. That does not equal 0. That's a negative 4. That tells me negative 2 is not a solution, only 6 is. And I won't know that unless I actually plug in and I check it. Now, let me give you a slight modification of this problem, just in case you encounter something like this. So this would be an additional example. Let's say everything about this problem was identical, except instead of having 0 on the right, let's say we had a 2. Then here's what would happen. We still have to isolate the radical, but when we do that, then we're going to have to move the 2 as well. So I would say if we go ahead and do what we did in the last example, add the radical to each side, then you would see we would have x equals the square root of 4x plus 12, but then we still have this plus 2 at the end. Now we would need to subtract 2 from each side, and we would have x minus 2 equals the radical. So we do have the radical isolated. It took a few more steps to get there, and we will still need to square each side in the next step. This is the part you need to be very careful about. We already know how to square the radical. That won't be difficult. But on the left side, you better remember you're squaring the entire side. So you need a parenthesis around the x minus 2, and then when you square it, remember that means x minus 2 times x minus 2. You're going to have to use FOIL in order to simplify that. The right side won't be a problem because the square will just eliminate the square root, but on the left side, you need to use FOIL. First, outer, inner, last. We're not going to complete this problem. I'm just giving you the heads up that if you had 2 terms on that side, when you get ready to square it, you have to remember to use FOIL. Okay, let's go to the last page of notes. And here's what we see. This time, instead of square roots, these are cubed roots. So you do see an index now in the corner. If it's anything other than a square root, there will be an index there. So just as we said before, we need to isolate the radical. And here's an example of having 2 different radicals. So we want to get 1 on each side. I'm going to add the cubed root of x to each side. When I do that, that leaves me with the cubed root of 5x squared minus 12x plus 6 on the left, and that's equal to the cubed root of x on the right. Now, in order to eliminate that radical, we're going to cube each side. So the left side gets cubed, the right side gets cubed, but since the only thing on each of those sides is a cube root, the cube will cancel out with the cubed root, and you are just left with 5x squared minus 12x plus 6 equals x on the right. At this point, this is very much like what we were doing solving quadratic equations back in section 1.4. So I would encourage you, let's get everything on one side. The easiest way to do that is to subtract x, because we do want to leave that x squared term to be positive. So I have 5x squared minus 13x plus 6 equals 0. You can decide whether you want to use the quadratic equation formula or whether you prefer to factor. Again, if we were to use the AC method, then that would mean that I'm looking for a pair of numbers that would multiply to give me 30. 5 times 6 is 30, and that's positive. My B value is negative 13. Now, I know I haven't really gone through this entire process with you in other examples, but I'll include it on this one in case you need it. That means if a pair of numbers is going to multiply to give me a positive, signs have to be the same. They're either both positive or both negative. If they're going to add to give me a negative, that tells me they both had to be negative, and the pair I need is a negative 10 and a negative 3. Now the way the AC method works, I'm going to come over here where we have a little room, and what we will do is replace the middle term with two terms. These two numbers we just found, the negative 10 and the negative 3, will become the new coefficients on our x terms so that we turn the trinomial we started with, the one that had 3 terms, into a polynomial that has 4 terms but means exactly the same thing. Hopefully you can see. If I were to add the negative 10x plus the negative 3x, I would have negative 13x. Now from here you factor by grouping. So if I look at the first pair, 5x squared minus 10x, I pull out the GCF. The greatest common factor would be 5x. And that means in parentheses, I would have x minus 2. I can check myself by using the distributive property, and I'll see that those are equivalent. Whatever the sign is in the middle, match it. I have a subtraction sign. And then when I look at the GCF of the second pair, the only thing they would have in common is a factor of 3. So that means that negative 3 is the GCF. In parentheses, I'm going to have x, and negative 3 times negative 2 will give me positive 6. I have to make sure if I use the distributive property, it's equivalent. And if I've chosen the right pair and I've done all this factoring correctly, what's going to happen is I now have two factored expressions, but they each have a common factor of x minus 2. Whatever is in the parentheses becomes my new common factor. That means this factors into x minus 2 times the parts that were the GCF that are outside the parentheses go back together in a separate parenthesis. So I have x minus 2 times 5x minus 3 equals 0. Again, you do not have to factor using this method, but if you've never really understood factoring, that's the AC method, and you can go back and review that factoring review lesson in more detail if you need to. I set each parenthesis equal to 0 to solve, so x minus 2 equals 0, or 5x minus 3 equals 0, which is going to give me two different solutions, x equals 2, or when I add 3 to each side here and then come back and divide by 5, I'm going to get the fraction 3/5. Now a very interesting thing happens with this one, and this check would be challenging without putting it into your calculator, and you will need to use order of operations carefully in the calculator. Both of these are actually solutions for this. It does not happen often that you get two solutions and they both work in radical equations, but this is an example of when that does happen. So let's move on to rational exponents. This is the last thing we'll cover, and then we'll be ready for our Chapter 1 test after we do our review. If we have an equation with a rational exponent that contains a variable or a variable expression as our base, then it will be raised to an exponent that is a rational number. So in other words, what we're going to see now will be fractional exponents. And the base that that exponent is attached to is going to have a variable involved. So if you look in the box, it says in a fractional exponent, the denominator is the index when written in radical form. the numerator remains the exponent for the expression. So this gives you an equivalent way of writing it. X to the 2/3 equals cubed root of x raised to the second power. The reason that's helpful is because you can actually simplify these equations without a calculator if you understand how to transfer it out of fractional exponent form into radical form. So let's look at the first example. X to the 3/2 power equals 216. Now the last part of what's in the box is very useful for us in solving this, because remember, we're trying to find out what x is. I really don't want an exponent on the x. But I do know if I were to take some base that's raised to a power and I raise it to another power. So for example, if I had x squared and I raised it to the 4th power, do you remember that a power raised to a power means I multiply those exponents and I would have x to the 8th? Since that's true, here's what I would ask myself. What would be the exponent that I could raise x to the 3/2 to, so that when I multiply those exponents, it would become an exponent of 1, because that's what I want, is x to the 1st power. Well, if you remember working with fractions, if I will raise it to the reciprocal power of the exponent, if I multiply a number times its reciprocal, I get 1. That's the strategy. So if I had x to the 3/2 equals 216, I want to raise both sides to the 2/3 power. Now, that's nice on the left side, because I know when I multiply 3/2 times 2/3, I get 1. So that's just x to the 1st power. But now I need to be able to solve 216 raised to the 2/3 power. You have an option here. If you have a calculator that has the ability for you to raise something to a fractional exponent, and again, it depends on the calculator you're using, so it might be something raised to the y over x power, or you might see the little caret or housetop sign that lets you raise things to a power. Perfectly okay to do that in the calculator, but I'm going to demonstrate without the calculator how you could solve this. Remember, the denominator in our fractional exponent is going to be the index when you go back to radical form. This is the same as saying that you need to find the cubed root of 216 and then square it. And you may think, well, I don't know how that helps me. If you remember, we have used prime factorization for simplifying radicals, and we can do that here as well. So if I were to take 216, do the prime factorization, that's an even number, so 2 is going to go 108 times. That is still even. 2 goes 54. Still even. 2 goes 27. No longer even, but I know a prime number that goes into 27, it is 3. 3 goes in there 9 times, and 3 will go into 9 3 times. Now that I have it factored with prime factors, whatever my index is, that's how many I would have to circle up to be able to come outside. Remember, we've been working with square roots. That meant that I was looking for a number I could multiply times itself in order to have something that comes out. That's what squaring something means. I'm multiplying it times itself. Since I'm looking for a cubed root, I need something that's multiplied together 3 times. So I notice I have 3 2's, but I also have 3 3's. 216 is a perfect cube. That means everything is going to come outside the radical, just as we did before. Whatever we've circled, we take 1 from each group, multiply them together, and that's what comes outside. 2 times 3 is 6. The cubed root of 216 is the number 6. And now I'm ready to square it. And 6 times 6 is 36. That's my answer. If I were to take 36, raise it to the 3/2 power, it would equal 216. And you could check that in your calculator as well if you like. Now the second example is slightly different simply because it's not just a variable raised to the fractional exponent, it's that variable expression, but we still have to get rid of that rational exponent. So if I were to ask myself, what would be the power I need to raise 2/5 to so that when I multiply those exponents it becomes 1. Well, it's the reciprocal power, so I need to raise each side to the 5/2 power, 5 over 2. And what I do to one side I have to do to the other, don't forget that. Well, the left side, again, those exponents clean up nicely, but instead of only being left with x, I'm left with x plus 7, because all it did is make the exponent become 1. On the right, I'm taking 4 and raising it to the 5/2 power. Think back to what we just did a moment ago. We can take this into radical form. That means that because the denominator is 2, I'm taking the square root of 4, and then I'm going to raise it to the 5th power. All right, I think you can clean that up. The square root of 4 is 2. 2 raised to the 5th power. If I multiply 2 together 5 times, I get the number 32. To finish this, subtract 7 from each side. And I now find that x is equal to 25. If I were to go back to the original problem and I put in 25 for x, the left side should equal the right. We are now finished with Chapter 1.